Hi, it's Mr. Anderson, and this is Environmental Science Video 6. It's on soils. Soils are incredibly important. It's where we grow our food, but they take a long time to form. We start with regular rock, and then over time what we have is weathering. We have physical weathering where we break the rock down into smaller particles. We have chemical reactions or chemical weathering. We have biological weathering as well, and so it takes a long time for us to go from rock to soil that we can grow our crops in. And the sad thing is that it can all be lost overnight. And so rocks, remember, are made of minerals, which are recycled on our planet using the rock cycle. They can undergo weathering, both physical and chemical, and that produces the particles in the soil. It makes up about half of the soil. We also have the biosphere contributing, life. We have the atmosphere and the hydrosphere, and also a lot of time. And so all of these contribute to soil. We're going to have lots of different types of soil on our planet. One way to look at classify soil is to look at the different horizons or the layers in the soil. We could also look at the particle size in the soil. Going from large to small, it goes from sand to silt to clay. Now that contributes to the porosity of the soil. How easy is it for the water to get down and bring water and nutrients to the roots of the plant? And then we also have the chemistry of the soil. Where did the parent rock come from? And one of the big things that's important in the chemistry is the CEC, or the cation exchange capacity. How easily does that soil deliver important ions to the roots themselves? Conservation is incredibly important with soils. We have soil erosion, where we're physically removing the soil, and then we also have salinization or salting of the soil, which is contributing to soil loss. So on our planet, remember, we have a rock cycle where we can move from igneous rock, which are crystallized magma, to sedimentary rock. So we have this weathering, erosion moves it, and then we have this compaction to form sedimentary rocks like sandstone. And then we can have metamorphism, where we're actually putting heat and pressure on that rock to convert it into a metamorphic rock. But it's weathering that contributes to our soils. First type of weathering is going to be physical weathering. This is an example of a rock that's been weathered physically. You can see it's just broken apart. So that's water. It could be ice wedging. It could be the roots of a plant. But anything that increases the surface area of the rock, in other words, anything that physically breaks it down into smaller bits, that's going to be physical weathering. Now that's only half of it. We also have chemical weathering. So on this rock here, you can see there's rust or oxidation going on the outside of that rock. And so that chemical reaction breaks down our rock into particles of the soil as well. So if we look at this granite, this feldspar here can react with naturally forming acids and form something called clay. And we'll talk about the importance of clay in a little bit. Now we can talk about soil being three phases coming together. So we've got solid, liquid, and gas. If we look at the solid phase, we're going to have the minerals of the soil itself. So that was the particles that came from the parent rock. We also have the organic material, so the living material, so roots would be an example, or dead material. We also have the hydrosphere, so the water coming together, and then we're going to have the air. And so this is the breakdown of how much contributes to the soil. It's going to differ on what soil we have, but if you think about it, what is soil? It's a coming together of the lithosphere, or the earth on our planet. It's also the air, or the atmosphere, and the hydrosphere, and then it's where we're headed next in this course. It's the biosphere, the living material. And so that's why soil is important. It's at this interface between all these different spheres on our planet. And if we look at how it's formed, bedrock is broken down, weathered over time, and we eventually get what are called the horizons of the soil. We could classify some of the major soil horizons. At the top, we're going to have what's called the O horizon. That's going to be the organic horizon. That's going to be where we're going to have a mix of a lot of dead or dying material. Below that, we're going to have the A horizon. That's going to be our topsoil. That's going to be a nice mix of minerals and also all the organics from the horizon above. As we go below that, we're going to have the B horizon, which is the subsoil. Not a lot of organics found in here. We're still going to have minerals and nutrients that are pushed down from the soil layers above. And then finally we get down to the C horizon, and that's going to be where we have parent rock. Now in certain soil horizons we'll also have an E horizon, and so that's alluviation taking place. In other words, we have the movement of water down, it's pulling those minerals out, and we're just left with sand and silt, kind of this dry layer. Particle size contributes to what type of a soil we're talking about. So this is a loam right here on the right side. So if we look at that soil, it's going to have varying sizes. We could go from very big like boulder to gravel, but eventually when we get to the level of the soil, we've got sand. Sand is going to be relatively large in the soil. We then have silt, And then finally we have clay. Clay is going to be particles that are smaller than 2,000th of a millimeter, so really, really fine particles. Now, what do those particles contribute to? It's the type of the soil and the porosity of that soil. So let's say we take those 3 particles and fill up a container with sand, silt, and clay, and then we fill it up with water. Well, you can imagine what's going to happen. In the container that has sand, it's going to drain out, or we're going to have high porosity, and that's going to take hours. In the silt, it's going to take days. And in the clay, it's going to take years. And so having a lot of clay can really stifle the movement of water into the pores where those roots need it. Now we can classify soil based on which of these particles we have. And so this chart takes a second to get used to. So this would be the clay on the left side from 0% to 100%. And this would be the silt on the right side and then the sand down below. Remember, in particle size, sand's biggest, then silt, and then clay. And so you can see on this chart that anything that has 50% or higher clay, we just call that soil clay. And we're not going to have good drainage, and this is not going to be a great place to grow crops. What's the perfect soil? Well, if we've got about 20% clay and we have about 40% of sand and silt, we have what's called a loam. And that's going to be a nice balance of all those particle sizes. Because clay is important. If we look at the cation exchange capacity, what's that? That's the ability of a soil to deliver important ions, important nutrients to the root itself. And the more clay we have, so this is going to be at the microscopic level, and the more organics we have, they're going to be attracting those cations and they're going to deliver it to the root itself. Another important property of soil that goes along with the CEC is going to be the base saturation. So how can these minerals buffer the acidity of the soil as it comes in as well? Because that acidity can damage the plants. Soil conservation, you can see, is incredibly important. If it takes hundreds of years to form these soils, we can turn that around overnight. So this is going to be soil erosion, where we're rinsing that topsoil off. And so as a farmer, you would want to mediate that. We can also have soil compaction. That's when, if the soil is wet and we're driving on it with heavy machinery, what we can do is we can compact those pores. And so that's going to destroy that soil as well. And then we can have salinization, so increase in salt. So if we've got plants growing on the soil, they're going to draw the water out and it's going to leave these natural salts behind. Normally not a problem because we're going to have rainwater. Rainwater is fresh water. And as we have that rainwater, it pushes those salts out. And so it's not going to damage the crops. Now, what's the problem if we start to irrigate? So now we're going to use irrigation and we're going to spray water on the crops. Where is that water coming from? It's not coming from the sky. It's coming from the soil itself. We're probably pumping it up. And so that means that those little droplets in the irrigation are going to have salts inside it. And so as that lands on the field, we're going to increase the salt levels to the point where we can't grow crops there anymore. And so how can we, solve this problem? We could flush it out with fresh water. We could change the type of crops we have, maybe get more salt tolerant crops, or we could use crops that have bigger roots so they can push that salt farther down. But you can see what I'm getting at. It's this idea that soil is a non-renewable resource. It takes a long time to form, and it's really hard to balance the proper chemistry and particle size in the soil. And this map shows us on areas on our planet where soil loss is vulnerable. And so it's important that we conserve our soil. So did you learn all of this about soils? Can you pause the video here and fill in the empty boxes? Let me show you what goes there. So the rocks and minerals are weathered, both physically and chemically, to produce soil. Along with the bioatmosphere and hydrosphere, this takes a lot of time. Types of soils could be characterized by the horizons or the levels. So we've got at the top O, A, sometimes E, and then B and C. We've got particle size. Sand, silt, and clay is going to be the smallest, and that leads to the porosity of the soil. And then the chemistry is important. CEC, or the cation exchange capacity, is incredibly important, and I hope that was helpful.